Good morning. In previous lecture, we have seen that how an object is represented in a feature space. If we have an object to represent, we need to extract some features from the object like this: F1, F2, F3, Fn. Then we construct a feature vector using these features, and this feature vector is called pattern. And this pattern is used for recognition purpose. Now question arises, how many features to select and which features to select? Selecting too much features will not help, because the training sample size required to train the classifier will also increase. Greater the size of feature vector, the requirement of training sample data will also increase. If this training set is small related to the number of features, then increase in the number of features can degrade the classifier performance. This effect is called peaking phenomena. Peaking phenomena. So it is always desirable to keep the feature size as small as possible without compromising the performance of the classifier. Now let us come to the example we have taken in the last lecture of making a classifier, of process of making a classifier that can classify boys and girls on the basis of their weights and heights. Suppose we have number of students spread in the feature space like this, and one dimension is denoting heights of the student and the second dimension is denoting weights of the student. Now how can we reduce the dimension of this feature space? Because here, for example, we have taken a 2D space. Now we want to reduce this feature space into 1D, one dimension. One of the solution of this problem is to select one of the features from weight and height. If we project these data point on the single dimension height, then let us see what happens. This point will be projected here, and this point will be projected here. This point will be projected here, and okay, like this, like this. Let us take the same example we have taken in the previous lecture, where we tried to construct a classifier that was able to separate boys from the girls on the basis of two features, and the features we have taken was weights and heights of the various students. We have to represent all the students of the class in a 2D space because we have two feature vectors. Then we can represent all the students like this. And for example, the combination of weights and heights of various students are as follows. These values are just for example. Then how we can reduce the feature space? We need to convert this 2D feature space into 1D. One of the dimensions is representing weight and other dimension is representing height. Now the intuitive approach to reduce the dimensionality of this feature space is that we can just omit one of the information from the feature vector. Now we don't have other dimensions. Suppose we select this W and we omit H. We are leaving this information, we are leaving height information, and we have only one information, weight. Now we don't have this 2D space, we just have a line representing weights of different students. Now if we are not having, because height information, all the points will be projected on this line only, like this. And these points are, you can see, these are very close to each other, and it is very difficult to classify students on the basis of weight only. That's why we have chosen two features to separate the boys from girls. We can see that points are very close to each other and one feature is not enough to represent all the students. Now we can see that projecting all the data point on a single line will not be able to represent the data points effectively. How we can represent the dimensionality of this feature space? We cannot select this W, we cannot select this height, because if we take this height as a feature and leave this weight, then the problem will remain same. If we select this height as a feature, then all the points cannot be individually represented on this line. So we cannot select W and we cannot select H, because selecting one of these two features will not solve our problem, because points will be very close to each other and will not be individually represented. Solution to this problem is principal component analysis. Principal component analysis. The solution is called principal component analysis. Principal component analysis. This is also called PCA, principal component analysis. These are our data points and these are features. This is a feature x1, this is feature x2. So we need to find a new dimension which is able to represent all the points individually. So this is a question, which line we have to select on which we can represent all the points. So it is very intuitive. If we select this line, let us call this line Z1, and we project all the point on this line, this Z1, then these points are adequately separated from each other. Now the problem is how to find this line. Now how to find this line? It can be very easily seen that this line is in the direction of maximum variance of data points. We can see that variance of data point is maximum in this direction, and if we select this line, then all the points can be very easily represented on this line. This line is called first principal component. And perpendicular to this is called second principal component. Let us discuss the process of finding these principal components. To find these principal components, eigenvectors are found from the covariance matrix of these data points. So first, we need to calculate the covariance matrix of these data points, by this formula. X minus mu X minus mu transpose, where X is a feature vector which is two-dimensional in this case, and mu is the average. Two lambda values, lambda 1 and lambda 2. Corresponding to these two lambdas, we can calculate two eigenvectors. Two lambda values, lambda 1 and lambda 2. Corresponding to these two lambdas, we can calculate two eigenvectors. Corresponding to largest eigenvalue is called first principal component. Eigenvector corresponding to largest eigenvalue is called first principal component, and similarly other eigenvectors are called second principal component, third principal component, and so on. In our case, we will get two principal components, and we can easily see that first principal component, means this direction, this Z1 direction, is able to represent our data set more accurate information, and second principal component is of second importance. Let us solve a practical problem. These are our data points: 2 1, 3 5, 4 3, 5 6, 6 7, 7 8. The first step is to find the covariance matrix. For that, we need to calculate X minus mu. Our mu is, in this case, 5.46. We have calculated this mu by just finding mean of these data points. X minus mu, let us calculate X minus mu. This is minus 3.4 minus 5. This X minus mu, Y minus mu, or let us call x1 and x2. So x1 minus mu, x2 minus mu, x1 3 minus 5.4, 5 minus 6, this is 2.4 minus 2.4 minus 1 minus 1.4 minus 3 minus 0.4 0. Now calculating X minus mu into X minus mu transpose. Minus 3.4 minus 5, its transpose is minus 3.4 minus 5, and this is equal to, I have already calculated, 2.41. After doing all this calculation, we will get the summation matrix by adding these matrices: 11.56, 17, 17, 25 plus 5.76, 2.4, 2.4, 1, and so on, all the 5 matrices, and this is equal to 22.36, 27.4, 27.4 and 40. And all these values, and this matrix is divided by 5 because we have 5 data points. Then we get the covariance matrix 4.472, 5.48, 5.48 and 8. Now eigenvalues and eigenvectors are calculated by this formula Ax equal to lambda x (4.472), taking this matrix 5.48, 5.48, 8, x equal to lambda x. This determinant. Now eigenvalues are calculated by this determinant. (8 minus lambda equal to 0). Solving this determinant, we will get this cross multiplication will be done. 4.472 minus lambda, 8 minus lambda minus 5.48, this cross multiplication, equal to 0. By solving this, we get the lambda values 4.31. We can solve this equation by using Sridharacharya formula to minus b plus minus b square minus 4ac divided by 2a. And by using this formula, we get lambda 1 equal to minus 0.431 and lambda 2 equal to minus 12.041. Lambda 1 is greater than lambda 2. We find eigenvector corresponding to lambda 1. Ax equal to lambda x. Using the covariance matrix 4.472, 5.48, 5.48, 8, x1, x2 equal to, taking lambda 1 minus 0.431 x1, x2. Rewriting this formula in this form, 4.472 x1 equal to, plus 5.48 x2 equal to minus 0.431 x1 and 5.48 x1 plus 8 x2 equals 0.431 x2. Solving these two equations, we get 4.903 x1 plus 5.48 x2 equal to 0. 5.48 x1 plus 7.569 x2 equal to 0. From equation 1, we get x1 equal to 7.569 divided by 5.48 x2. This is equal to 1.117 x2. Let us draw these points on 2D space. One, two, three, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 1, 2, 1, this point. 3, 5, 3, 1, 2, 3, 4, 5. It will come here. 4, 3, 1, 2, 3, 4, will be here, and 7, 8 will be here. So these are the original points represented in a 2D space. Now let us find the line by taking the first principal component. This value was x1 equal to 1.117 x2. If we take x2 equal to 1, then x1 will be 1.117. So the vector corresponding to this value will be 1.117, 1. So this vector will, let us draw this vector 1.117 and 1. If we take x2 equal to 1, then x1 will be 1.117. So the vector corresponding to this value will be 1.117, 1. So this vector will, let us draw this vector 1.117 and 1. The direction of this vector is this, and if we extend this vector to get the line, we will find a line which is able to represent all the data point in the set. So we need to select only one principal component to represent all the data set, and second principal component can be left. This principal component is representing much of the data set information. Thank you.